Hi, Steve Ellingson here from Virginia Tech. This talk is about adding electronically reconfigurable surfaces to large reflector antennas. But first, let me say a little bit about how this idea comes about. The idea stems from the problem of interference in radio astronomy. There are likely other applications, but what we've developed has been developed in this context. In radio astronomy, there is the problem that satellite downlinks interfere with observations. The traditional ways to deal with this are, first, avoid observing when a problematic satellite is present, or second, if you can't avoid the satellite, then try to edit the interference from the afflicted data. The editing is normally done as an operation on the dynamic spectrum, and usually consists of modifying pixels in the time-frequency plane that seem to have interference in them. In the future, and perhaps in the near future, it seems likely that these traditional techniques will not be sufficient. The principal culprit is the emerging category of megaconstellations, Starlink, for example, which aim to have tens of thousands of satellites, all transmitting at radio frequencies from low Earth orbit. This may well take the avoidance strategy off the table, since at least a few, and perhaps many satellites, will always be in the sky no matter where you are on the Earth. A legitimate concern is whether time-frequency excision might also be overwhelmed, because one may end up having to remove so much data that what remains is not suitable for scientific interpretation. So we think of ways that the telescope can continue to observe in afflicted time-frequency pixels. That basically means looking through the interference as opposed to simply avoiding it or deleting it. Two such approaches are coherent time domain canceling and array signal processing, such as adaptive null forming. A review of these topics is beyond the scope of this talk, but suffice it to say that there is no free lunch. For each of these methods which give you a look-through capability, there are problems remaining to be overcome. First, they need to be able to work well at low signal-to-noise ratios, and broadly speaking, they don't. Second, these methods have the unfortunate tendency to distort the astronomical signal and also color the noise in which the astronomy is embedded, and that might not be better than the interference that you were trying to get rid of. So, the technology I'm about to discuss aspires to be a solution to all that. The key idea is that because reflectors tend to be large, and therefore the beam is very narrow, the satellite signal is usually incident from the side lobes. So, let's see if there's something we can do to move side lobes into a pattern that puts the satellite downlink into a null. The notion is to take some fraction of the outer portion of the reflector and turn it into a reflector ray of some sort. We're calling this electronically reconfigurable scattering, or ERS for short. The idea is shown here in the way it might be implemented on an axisymmetric prime-fed paraboloidal reflector, although the idea is certainly not limited to that kind of system. Although there is no particular reflector array implementation that we have in mind at the moment, all we need is for the surface to consist of unit cells, and we need to be able to manipulate the phase of the scattering from each of the unit cells individually. A good way to think about this is that you start with all the cells in the same state, so there is essentially no change from before the rim was replaced with a reflector array. Then a satellite shows up, and you find a set of element states that changes the overall pattern so that there is now a null in that direction. If you don't use too much of the dish, then the main lobe gain and the shape will not change very much, and perhaps those two could also be constrained. To demonstrate the concept, I'm going to use an example with these parameters. The overall diameter is 18 meters, the f over d is 0.4, For the purposes of the demonstration, a simple feed model suffices, so we'll just use a short dipole with a modified pattern to give us an edge illumination of about minus 11 dB, and subsequently an aperture efficiency of about 81%. In this example, we'll give up the outer 50 centimeters to the reflector ray, which equates to about 11% of the projected area of the dish. And we'll do the study at 1.5 gigahertz. At that frequency, it takes about 2,750 elements, presuming the elements are on a half wavelength grid. A good question to get out of the way is whether the loss of aperture to the reconfigurable surface is acceptable. Well, on the right here is the H-plane copole pattern for the original dish, and also for the modified dish, assuming the worst case, that the reconfigurable surface can't contribute at all to the system gain. Of course, the difference is small, but it is significant, especially once you consider that there will be a loss associated with the radiation efficiency. That is, the elements will likely burn up some fraction of the power incident on them, as opposed to scattering that power. Of course, the actual numbers depend on the reflect array implementation, but out of the gate, this issue doesn't seem to be a showstopper, even if not compensated. The next question you might ask is whether a mere 11% of the dish is sufficient to null side lobes. And the answer is that it is. The way we answer that question is simply to do a physical optics analysis of the system, treating the reflect array elements as patches in the PO surface integration. And then what we can do is adjust the phase of the field scattered from each of those patches to model the action of the reflect array. What happens in an actual reflect array is, of course, slightly different from an electromagnetic perspective, but that's not a big concern at the moment. Here we're just trying to determine basic feasibility. The plot on the right shows the pattern of the central 17-meter non-reconfigurable portion of the dish, starting in the center of the main lobe and going out 2 side lobes. In each direction, we've worked out the new gain in that direction after having set the phases of the elements to maximize gain from just the reconfigurable surface. The solid black line is what you get if you have fully independent and continuous phase control. What you find is that you can access enough scattered power to meet or exceed the power scattered from the non-reconfigurable part of the dish, beginning somewhere at the edge of the main lobe. Of course, if the element phases are quantized, then you lose some performance. The red line is what you get if you have 2-bit phase control, that is 4 phase states, and the blue line is what you get if you have 1-bit phase control, that is just 2 phase states, for example, 0 degrees and 180 degrees. You can see that you can easily overcome the second and subsequent side lobes, and that with sufficiently fine control you can overcome parts of the main lobe and the first side lobe. Now, note that these are pessimistic estimates, since we are not actually trying to maximize gain in some direction, but rather minimize the gain of the sum of the main reflector and the 2,750 elements, which is not exactly the same thing. But we'll demonstrate that in a moment. Here's an example of performance from the system. The pattern of the original 18-meter dish is shown as the dashed black line. Next, we use the ERS to force a null at 1.75 degrees, which is the peak of the second side lobe of the original system. We'll assume 1-bit phase control. To calculate results, we need an algorithm to set the element states. The algorithm used here is called serial search, and it is just the simplest thing that you can imagine doing. All you do is you go through the elements one by one, and you set the phase based on whether the gain in the direction of the desired null goes up or down. When you've done that for all the elements, you stop. The result after serial search is the blue solid line, and the thing to see here is that we have in fact put a deep new null exactly where we intended. So the method works even using the simplest possible method. The news, of course, is never entirely good, and one thing we see here is that we now have cross pole, that is the dashed blue line, where previously we had none. However, the level is quite low. One other interesting thing to see here is what the serial search algorithm gave us for element states. This is shown as the ring shape on the left of the plot. This is a map of the rim color-coded by element state, red or blue, representing the 2 possible phases of the element at that location. So there are 2,750 pixels on this map. What you see is that the phase states are highly ordered. This is encouraging because it suggests the thing that you might have already suspected. That is, that there may be a deterministic starting condition that can be used to speed up the process of finding the element states. Speedup was not required in this problem, but you can imagine that once we begin adding constraints, this will become an issue. So, we'll be looking into the initialization problem, but first we're looking at multiple constraint algorithms with no such smart initialization. The reason we're interested in other algorithms is because we don't want to just move nulls around, but we also want to constrain the main lobe gain, and we also want to constrain the shape of the main lobe while we're doing that. In other words, what we really have is at least n plus m constraints, where n is the number of nulls, and m is the number of constraints that we'd like to put on the main lobe. Serial search is probably not suitable for that. My collaborator, Mike Buer, has been looking at various ways that we can set the element states with multiple constraints, and you can see his work in the preprint identified here. He's identified a number of algorithms which are very attractive, but which unfortunately require continuous, that is, not discrete, control of element phase and magnitude. The problem is that when you quantize magnitude or phase, you can't solve directly for the element states, and you end up having to do some form of iterative optimization. The algorithm we've been using is simulated annealing. Simulated annealing is a bit difficult to explain briefly, but you can get the rough idea of what it is from this graphic, which shows the famous traveling salesman problem in 3 dimensions, being solved by simulated annealing. Like our problem, the traveling salesman problem forces you to sift through a large but discrete set of possible solutions, but you don't have the time to do the exhaustive search. So instead, what you do is you change the behavior of the search depending on how close you think you are to an acceptable result. Here's an example of simulated annealing applied to our problem. Here we're constraining the gain of the dish to that of the non-reconfigurable 17-meter dish. It is certainly possible to set a higher gain, but for this exercise we want to make sure that a solution is possible. Simultaneously, we want to drive a null between 1 and 3 degrees, that is somewhere in the first 3 side lobes. Here we assume 1-bit phase-only control for the elements, and we also look at 2-bit phase-only control. And we're doing 100,000 iterations of simulated annealing, which takes on the order of 10 seconds or so on a general-purpose computer with nothing at all done to optimize speed. On the bottom right, you see null depth as a function of null location. Note that deep null is achieved no matter where in this range of angles you choose to put that null. Now, you might wonder why the null at around 1.2 degrees is not as deep, and that's because 1.2 degrees is the peak of the first side lobe. So at that location, we're starting to run out of ERS aperture. This is evidence that the 50 centimeter width of the ERS is just about right. That is, we've got enough area here to achieve solutions, as shown here, but not much more. On the top right, you see the main lobe gain as a function of where the null was driven. Here we see more good news. The main lobe gain has been held very steady as we have requested. It's hard to see on the scale, but the variation is less than 1/10 of a dB, certainly inside the accuracy of the PO analysis that we're doing here. So, all of this bodes very well for the efficacy of ERS side lobe control technology. You might fairly wonder about the bandwidth of this method. If you do nothing to optimize over frequency, the bandwidth is mediocre, as you might imagine. That's what this plot is showing. Here we're looking at the gain in the desired null direction as a function of frequency. Depending on how you define bandwidth, the bandwidth of this null is somewhere between 0.5% and 3.5%, which at this frequency is somewhere between 7 MHz and 53 MHz. That might actually be sufficient for the particular signals we're dealing with at this frequency. However, we don't need to settle for this, and that's because there's every reason to believe that bandwidth can be dramatically increased simply by implementing some additional frequency domain constraints. And the ERS reflect array certainly has plenty of degrees of freedom available to do that. One final result I'd like to show is how the overall pattern changes with frequency. On the left is a pattern optimized at 1.5 GHz and then plotted at 1.5 GHz and 1.42 GHz. You can see that there's some jostling about, which of course is totally expected. What is interesting is that if we increase the degree of element control from 1 bit to 2 bits, that is from 2 phase states to 4 phase states, then you get the result on the right. So with no additional optimization, you get much less frequency variation if you increase the degree of control, even if you make no attempt to optimize over frequency. So that's a potentially useful thing to know. Finally, some concluding remarks. First, the ERS concept appears to be reasonable. We've hardly done a comprehensive feasibility study, but what we have done reveals no showstoppers, at least so far. In particular, we see useful levels of performance for even the crudest forms of element control and algorithms. It appears that we can exercise very tight control over the main lobe while doing this, which addresses a primary concern for the use of this technique in radio astronomy. Also, recall that the system example presented here has -11 dB edge illumination. That optimizes effective aperture, but is somewhat higher than what would typically be implemented in a radio telescope. In radio astronomy, a more typical number would be something like -16 dB, in order to mitigate an increase in system temperature from spillover. Now, at first, it seems like decreasing edge illumination should be a problem, since the ERS needs to access a certain amount of power in order to do its thing, and decreasing edge illumination certainly works against that. However, there's a surprise. We've analyzed the -16 dB case, and we find that everything works just as well. That's counterintuitive, but it turns out that the loss of power available to the ERS is nicely offset by the associated loss of power available to the much larger non-reconfigurable portion of the dish. So, ERS technology appears to be robust to varying degrees of edge illumination as well. Some other things to note. ERS technology is very robust to element failures. Basically, the main lobe is not affected even if a large number of elements in the reflector array fail. For additional assurance, one can take the usual precautions to ensure that elements fail in a specified state, so that a failed element simply reverts to being a portion of the original fixed, non-reconfigurable dish surface. As I've already pointed out, the ERS reflector array provides a very large number of degrees of freedom, so we're just beginning to scratch the surface of what can be done in terms of number of nulls, main lobe shaping, side lobe constraints, frequency constraints, and so on. Of course, I should also mention items of concern that remain about this technology. As I showed, bandwidth is perhaps okay, but nevertheless small if you do nothing to address it. What I did not mention is the multi-frequency problem. For example, if you use this dish at both L-band and X-band, and you want to be able to steer nulls at both frequencies, well then you need elements that can support that. So there's a non-trivial problem in reflector array design remaining to be addressed. Also, computation, for example, for simulated annealing, is formidable, but it's really not unprecedented. A somewhat more serious problem, in my opinion, is that we may not know the pattern of anything sufficiently well in advance, which means that we're going to end up, in effect, having to solve for patterns simultaneously with the element state solutions. That's probably going to require a closed loop approach, where we are trying solutions and evaluating performance simultaneously in real time. Finally, let me point out that preprints are available, indicated here, that go into detail on many of the issues I've skimmed over in this talk. That concludes my presentation on pattern control for large reflector antennas using electronically reconfigurable rim scattering. Thanks for listening.